Hello, everyone. To make a functional quantum computer, we need to be able to transform qubits into states that are required to get the computational task at hand going. We need to work with reversible transformations that preserve properties such as the normalization of the qubit state. In this video, we will introduce unitary operators which are analogous to isometric operators in the study of vector spaces. Here we have the general state for one qubit, labeled ket psi. A unitary transformation of ket psi, represented by u with a hat, transforms it to ket psi prime. This is the equation that represents this transformation. In terms of matrices, it can be viewed that way. So u is represented by a 2 by 2 matrix. For u to be an acceptable operation on the qubit, it has to satisfy the relation u dagger times u equals the identity matrix. In other words, u dagger is equal to the inverse of u. A consequence of that is that ket psi stays normalized after the transformation to ket psi prime. Also, the u transformation preserves inner products. So, let's say u transforms ket phi to ket phi prime and ket psi to ket psi prime, then the inner product between phi and psi and phi prime and psi prime are the same. In quantum information, these unitary operators are called gates. So what are some examples of these gates? Let's start with one qubit gates. This is the bit flip gate. It flips ket 0 into ket 1 and vice versa. Then we have the phase flip gate, which multiplies the ket 1 part of the qubit by -1. And finally, the Hadamard gate, which creates superposition states, making ket 0 into a state proportional to ket 0 plus ket 1, and ket 1 into a state proportional to ket 0 minus ket 1. Next, let's talk about quantum circuit diagrams. These are visuals that represent qubits and qubit operations and become super helpful when a computation involves many intricate and intermingled steps. So let's start with the qubit representation. Yep, it's just a horizontal line. The left end corresponds to the initial state of the qubit and the right end to the final state. The evolution of the qubit state in time is from left to right. Well, here there's nothing going on. The initial and the final states are the same. But if we add an operator, the state can change. This is how an operator U is represented in a quantum circuit diagram by a box. Let's look at the example of the X or bit flip gate. If the initial state is ket 0, X will transform into ket 1. Now let's look at an example of a 2-qubit gate. This is the C0 gate. It's a universal gate, and universal gates are qubit gates that allow the creation of entanglement of any quantum state you can think of. What it does is it changes the state of a qubit called the target qubit dependent on the state of a control qubit. This is how the C0 gate is represented in quantum circuit diagrams. The circle with a plus sign labels the target qubit, while the black dot labels the control qubit. Either qubit can be the control or the target. Just make sure you label the diagram properly. This is how the general 2-qubit state is transformed by the C0 gate. Notice how only when the state of the control qubit is ket 1 does the state of the target qubit get flipped. Here's an exercise for you. Show that the general 2 by 2 unitary operator has this form: A, B in the first row, and minus the complex conjugate of B and the complex conjugate of A in the second row. Bye bye.